Greetings, my friends.
Morning.
Greetings, greetings. Let's see what I want to show you. What I did on this page. Why isn't it showing up? There it is. Oh yeah, I should show you that. Awesome. I'm saving something really quick as a PDF file so I can show it to you guys. Drag it over. Bam, there it is. Engineering. Well, yeah, we need that. Okay, let's share screen and get on with it. Golden. Okay. Awesome. Alluded to this a little bit the other day, but let's get into it now. So really looking at 14.4 and 14.6. Which is really about power, which is kind of taking the energy concept to another level. And what it really best defined is, well, and this I think will make some sense to you. I spent a little time last time trying to help you at least get a kind of better understanding of why anybody would even ask these sort of questions, or where these formulas would kind of come from. I just find personally, if I don't have some context, I have a hard time connecting with the material. But this is kind of what I alluded to last time. Really, power comes down to not just work. We said work was a force times a distance. Like, hey, I lifted all those bricks up on top of the roof. It's like that was a lot of work. And so it was a weight and a distance I lifted it. And so again, we saw that made sense because it would sort of be, harder to move the bricks 20 feet in the air than it would be just to lift them 3 feet in the air. So it's not just force, but it's a force and a distance. And so that's why somebody, made up a name for that. So that's fine. And now this is actually considering time. It's like making a rate out of it. Like, that's great. You lifted those bricks onto that roof, but it's like, how long did it take you? How much time's involved? And so that's what power is really like considering time. And so, we need a car with enough power to get up that hill. So that's a word that's in your regular everyday language, or, somebody's in the gym and they're a power lifter. And so, or, a motor has a power, any motors that have, anyway. So we said work was a force times a distance. Force was in newtons, or let's see, I guess that could also be pounds. Is that right? Force is newtons. Yeah, force is newtons, force is pounds. And then it was times a distance in meters, or in the case of our system, times a distance in feet. And now we're dividing by time, which is commonly seconds. And so that's what force is. Or that's what power is. Power is in metric, Newton meters per second. And so again, notice you get kind of crazy units for that, or foot pounds per second, or pound feet per second. And so, what are those units really referencing? And so if you notice in my note sheet for this time, notice we have some, units for that. And so that has been renamed foot pounds per second. That's what's renamed as horsepower. And again, that's probably a term you've heard before, at least in context of a car or something like that. Or Newton meters per second. So that's been renamed as watts. And so that's how power is commonly measured, is in watts. And I don't know if you've ever looked at a power bill before, but that's kind of what happens. You're paying for actually not a watt but a kilowatt, which is 1,000 watts. And so a watt is such a tiny amount of electricity that you don't even pay for that. A kilowatt is like 8 cents. 1 kilowatt of electricity on your phone, on your bill, is like 8 cents. And so it takes 1,000 watts to kind of even equal very much money.
Don't they charge in kilowatt hours? Because you can charge get 8 cents for a kilowatt. Would that be like for half a second of power draw or 12
Well,
hours of power draw?
well said. That's exactly right. It depends on how many hours it is. So it's actually not just a kilowatt, it's a kilowatt on per hour. So if you have 1,000 watt light bulb, that'd be 1 kilowatt. If you left it on for an hour, then that cost you 8 cents. So you're exactly right. It's over the time of an hour. And so notice watts is a reference to time. It's got time in it. So, you've probably looked at a light bulb. I have some bigger ones in my garage and they're 200 watts and I have like 11 of them. So that's a lot, it's a lot of watts. And so let's see if I just punch a few buttons here. If I take 11 times 200, 11 times 200, that's 2,200 watts. Well, that's 2.2 kilowatts. So that means if I left all those lights on for an hour, again, it's 8 cents for that. So if I say times 0.08, that's like $1.76. I'm sorry, like 17.6 cents. It's 8 cents a kilowatt. That's only 2 kilowatts. So it's like 16 cents. It's actually 17.6 cents. But lights actually don't draw that much electricity. And so in the end, that's how all the appliances in your house are measured. I'd encourage you to do this if you've never done it before. But like when you get off, like go look at all the stuff in your house that's electric. It'll actually say on it how much, what its power draw. In other words, what kind of power does it take? And you can probably appreciate as an electrician that if you need to know what's going to go there. In other words, an oven, anything that heats things like water heaters and ovens, that takes a lot of power to heat. And so those things will take a lot more kilowatts of electricity. And therefore, if you know that, then you got to put a bigger wire, you got to put a bigger pipe, if you will, to take electrons or electricity to that appliance. And your meter is going to spin when you got that oven on, but it's not really going to spin too much when you got lights on. So that's just interesting. And so the point is that we kind of interact with this kind of stuff a little bit. So horsepower is our system, and then watts is metric. And then it's kind of cool to, I don't know why you just stopped sharing, but it's kind of cool to actually convert between the two a little bit. And that's the one last thing I wanted to show you on there before it timed out, because I wasn't doing anything. Let's start writing and start making some sense of this stuff. So that's this right here, 1 horsepower. So the unit is called horsepower, but it actually takes 550 foot-pounds per second to make 1 horsepower. And of course, you can probably appreciate that the history of that goes back to horses, and probably when they came out with the iron horse, the tractor. It's like, wow, that tractor, that can do the job of 12 horses, that can do the job of 18 horses. And so you can see how they named tractors in terms of horses, or maybe it had to do with trains, and like a 4 horses can pull this cart. How does a train do? And so it's interesting because like the original system was designed on just comparing it to what a horse can do. That's kind of interesting. So somebody defined that. And again, I'd give you some extra credit in this class to bump you over to the next grade if you go investigate that a little bit, find something on Google and look it up. And why is it 550? Why did somebody come up with 1 horsepower is 550 foot-pounds? That feels kind of random to me. Why wasn't it 400? Why wasn't it 900? Like, where did that come from? Did they measure a horse somehow? Did they give it a certain number of pounds and then have it kind of walk a certain number of feet and see how long it took in a second and average that out? Is that where that came from? Is it that simple? And then as far as a conversion, you can even convert that to watts. So it's important to understand that this is kind of the standard system number, and this is sort of the metric number, but they're both speaking to the same thing. They're both speaking to power. So it's kind of interesting that your house is in watts, but your car is in horsepower. Isn't that kind of strange? So anyway, let's play with that for a little bit here. So watts, this has been renamed a watt. And this has been renamed horsepower. And so we'll use some of those conversions in just a minute. I bought a kind of a dream car about 6 months ago that I've always wanted to find, a 66 fastback Mustang, and it's 225 horsepower. That's what the motor is. I kind of, looked into it a little bit. 225 horsepower motor. I don't have the ability to show this to you, but just out of interest, I got online and looked at some of the most powerful engines that exist out there. And like one of Ferrari's got 650 horsepower. So that's like triple my little sort of 1960s family car. A later version of a hybrid version of Ferrari in 2015 got up to 963 horsepower. So again, those are just reflections of how powerful the motor is and so forth, like what it can do, what it can get done. It can do the work of 225 horses in a sense. That's pretty cool. So that's what this is getting at. It's not just work, it's kind of work over time. And so just to have it written here, what I had in my notes, because we'll need it in just a second, we said that 1 horsepower was equal to 746 watts. And we said that was also equal to 550 foot-pounds per second. That's kind of all the conversions a person would ever need, if you will, to kind of make these calculations work. So let's take a look at kind of a practical example. I've mentioned a time or two in this class that I love riding my mountain bike, and that's kind of where this gets practical to me, in the sense that, well, I weigh about 180. My bike weighs about 30 pounds, and so that means my bike and I weigh 210 pounds. So I got to haul that up the hill, right, when I'm mountain biking. And so I'll say that's the biker. And let's say I go out on a climb and I climb, and this is kind of a real common thing to do. Let's say I climb, I don't know, 2,500 foot climb. Now, what you should say is, well, that's a lot of work. And again, that's a vertical elevation. I might be going up a road like this to get there because I'm not strong enough to kind of paddle up this road, or it might be, just barely uphill, and I might have to go like 50 miles to climb that high. But the end result is, because gravity is straight down, the only thing I actually care about is how much vertical is there, because it's going to be a certain amount of work. So notice I have feet, I have pounds. That's going to be a lot of work to lift 210 pounds, 2,500 feet in the air. So there's work right there. The units are already correct. But of course, where power comes in is like, it turns out I'm like a crappy mountain biker. Why am I a crappy mountain biker? Well, because it takes me forever to do that. Whereas somebody who's a good mountain biker, powerful, you might say, takes, well, a whole lot less time. So let's say that I climb that in a time of, I don't know, 28 minutes. It took me 28 minutes to climb that. Well, now we can actually talk about how powerful, you are, how good of a mountain biker. So do you see why all of that together, both the work done and the time involved to do it? Can you see why people would naturally want to know that, and why, we measure motors based on not just how much work they can do, but how fast they can do it? And so, well, we just figured out, we know what to do here. Like, we know the answer to this is feet times pounds divided by seconds, right? So don't I take feet, 2,500 feet times 210 pounds. What's wrong with what I'm doing right here? So make sure you guys are live. What's wrong with that?
Minutes.
I need seconds. So if I multiply by 60, then that would be feet, pounds, seconds. Okay. So now I'm about to get a number that I can actually kind of compare well to horses, I guess you could say. I can compare this to like my car, my 225 horsepower engine. Like, am I comparable to that? Like, am I as strong as that engine? Well, let's find out. 2,500 times 210 divided by 60 divided by 28. I got 29.8. 29.8 what? What's that unit?
Horsepower.
It's not directly horsepower. It's kind of horsepower, but it's right now it's actually still foot-pounds per second, because notice it actually takes 550 foot-pounds to make 1 horsepower. Oh, that's bad news. So I'm not even 1 horsepower. Does that make sense? Well, of course I'm not. Like, am I as strong as a horse? No. Of course it's less, right? Does that make sense? So if you did want to convert this to horsepower, does it make sense that you need to, well, multiply by units that would be foot-pounds per second and then horsepower on the top? And there's my conversion. 550 foot-pounds is 1 horsepower. Bad news. I got to take my number and divide by 550. It's very depressing. Yeah, 0.05. There's my horsepower. That seems wrong. It is wrong because this isn't 29. I'm looking back at my calculator and I didn't type. I said 210, but I didn't type 210. I typed 20. So I'm going to go back. I didn't think I was that bad. So it's actually 312.5. I just multiplied wrong. And if I divide that by 550, I get 0.56. So I'm actually 0.57 horsepower. What does that mean? It means I'm half of a horse. And by the way, I actually don't think I could do that. I don't think I could actually climb 2,500 feet in 28 minutes. I don't think I could do that. So I'm less, actually. So that's kind of cool. And so that's how we measure it. And so all measurements are kind of like that. They're always relative to something else. And so, it's all turns out to be kind of relative to horses in a sense. And so that's kind of the concept here. So that conversion is pretty legit. In other words, I really got to stare at that. So I could convert it to watts too now if I wanted to. But we speak this way. And so now I think about my car and I think 225 horsepower. Wow, that's like 500 or 450 times as much as me. Well, again, of course it is. Like, you've driven a car up a hill. It doesn't seem to struggle as hard as you and I do, right? So that's pretty impressive that we invented a machine that can actually do that much work, considering I can only do half that much work. Now, let's add one more thing to this that's kind of interesting based on this formula sheet. Let's add one more thing. There's one more thing that you need to know that's on our notes right here, and that's this guy right here. Efficiency. Efficiency with kind of a little curvy E is equal to power input divided by, power output divided by power input. Frankly, a better way to say this, a better way to write this formula so that it makes sense to you would actually be to multiply power input to the other side. In other words, if you take your efficiency, like let's say my bike was 85% efficient. Does that make sense? There's waste involved. Like, for instance, in a car, if you put gas in there and the gas explodes and so forth, and now you have this piston getting pushed. Well, that piston getting pushed has to be transferred through a system of gears, through liquid and so forth, back to your back tire. And so you actually don't get all that. You don't get all of the explosion turned into your car going down the road. Same with my bike, like this change stretches. Bikes are a lot better, but change stretch, and you might not get all the power out that you actually put in. So if you take 85% of whatever 30 horsepower or something like that, 85% of that. You might not, you don't get all of that coming out. You see what I'm saying? That's what this formula is really getting at. And so the reason that's important for an engineer to think about is, you know, you have a certain amount of work you need to get done to say lift something up, but like if the motor is not perfectly efficient, then you got to get a slightly bigger motor. Does that make sense? So one other thing I want to show you that's kind of cool. Not that, that. So I do lots of house related stuff. Take a look at these. Well, here's your choices for some garbage disposals. What do you notice on there? Why am I bringing this up? Why did I bring these here?
All measured in horsepower.
Yeah, notice like what makes them what they are is this is a 1 horsepower. This is a 3/4 horsepower. There's another 3/4 horsepower. There's 1 1/3. Ooh, that's more than 1 horsepower. Awesome. This little wimp is only 1/2 a horsepower. This is 3/4. That's a half. That's a half. So, you know, some of those are twice as strong, if you will, more than twice as strong. Notice that isn't always reflected in the price though. Notice the largest one, the old Badger there, is only $89. So that's kind of interesting, isn't it? So obviously there's, you know, there's more to it in terms of how long is it going to last? Is it stainless steel, that kind of thing. But, you know, one of the things you're going to want to care about is, you know, how strong is it? How much work can it do? And so that's what you're being told. You're actually being told it's horsepower because, you know, it's got work to do. What about this? The other thing that I often spend time with, table saws. I've had table saws where I feed the wood through it and it can't turn the blade anymore. Like the wood is wet and the blade maybe isn't sharp enough and the blade just comes to a stop. It's like not powerful enough to cut that wood. Well, again, notice what you're seeing here. This is a 5 horsepower, way stronger than an Syncerator. It's like got a real big job to do. That's 5 horsepower. This one's only 3 horsepower, etc. Look at this little limp. It's only 1.75 horsepower. It's like almost the garbage disposal motor is in that one, right? Like that one was 1 1/3. So, but you see what I'm saying? Like that's an expression that people can relate to. Now, again, it's kind of funny to think this table saw can do the work of 1 3/4 horses and so forth. But these are expressions of power. Like this is what it means. And so, you know, we're touching all that. And of course, you know, as an engineer, you're the one that's got to design the motor, right? You're the one that's got to stick the motor on wherever it is you're drawing. That's how you're hoping to get paid, right? And I won't go into this, but notice, for instance, this one is 5 horsepower. And it says down here that it's 230 volts. In other words, that's a reflection of the fact that you're going to need a larger wire going into this. That does not plug into your wall. Your wall outlet is 110 volts. So that won't plug into your normal wall outlet. It's a powerful motor, but you got to feed it, right? You got to give it something. You got to give electricity. And so I don't know how much you understand about all that, but notice this one over here, this little wimp over here that I pointed out, this one actually has choices. You can do a normal outlet, 110 volts, or apparently it also works on kind of a larger circuit as well. So that's kind of cool. But anyway, that's what horsepower is. Oh, actually, I do have this, I guess. So there's some of the cars I mentioned earlier. I didn't realize I had that. So it's like, yeah, those are way more awesome than my little wimpy 225 horsepower fastback. Oh, what a beautiful car that is. So let's consider that with my bike problem, just to kind of see if we can actually, you know, make some sense of that. So this is, what would you say this is? Is this power out? Or is this power in? Which one is that? So if I said my bike was 85% efficient at converting the power into actually work, am I going to say that this is 0.85 equals 0.57 over power let's see, I think it was, I forgot already, was it power output? I forgot. I guess I'll have to look. Shame on me. Power in was on the bottom. Is this the equation, or is it actually 0.85 equals power output over 0.57? Like, which one of those do you think it is?
The right one.
How confident? How much would you bet? I give you $100. Would you bet 100 of it, or would you bet 5?
I'm a student, so let's do $5.
Give me 95. Well, would you agree this actually happened? Does that make sense? Let's pretend a motor was doing this. That actually happened. 2,500, 210 pounds got carried to 2,500 feet in 28 minutes. Like, that actually happened. So is this the motor then? The answer is no. Like, that's what the motor put out. That's the output. That's what it put out, because that's actually what got done. And I don't think that's obvious. So you just made 95 bucks, Evel. It's a good thing you only bet 5. Do you see the logic in that? This isn't always obvious, I guess, is what I'm saying. So it's like, again, think of this as a car. If you have a car that has 225 horsepower in the motor, well, what if it's terribly inefficient at, turning that motor into, because remember, you're just going to attach it to a bunch of junk, a bunch of gears and so forth. So basically, you're just not getting all of that out of it. So, if you got a job to do, like this is actually, this happened, like this was the job that got done. And so in the end, what this is saying is if I solve this equation for the power input, in other words, the motor's power, I just think input sounds weird. That's why I'm kind of highlighting this a little bit. I could see a person getting this backwards. Basically what this means is you need a motor, which is kind of again, this just feels weird to say input, I think somehow, but basically this means if your motor was only, or if your bicycle, not so much your motor, but your bicycle and the chain and the gears and all that was only 85% efficient, then you'd have to have a larger motor on your bike, a 0.67 horsepower motor, since you're going to lose some, because that's actually the job that needs to get done. Does that make sense? Well, let's do an example. Kind of a book example. This will prepare you for some of the assignment in this section. So stare at this question for a second. This is in your book. Just took it straight out of your book. So here's this car going up a hill, and of course you think, yeah, this is an example of power, because as I mentioned before, it's like a car heading up a hill, and notice it's a 7-degree hill. And it has weight. Notice that says megagrams. That's not good. We really need that to say kilograms. Why do we need to say kilograms for that? Why do I need to do that? Why don't I just leave it megagrams?
Because all the other units use kilograms.
Yeah, because Newton is kilogram meter per second squared. And so, yeah, exactly, Daniel, all the other units. And so that's how much it weighs. And so there's the load, there's the thing we're lifting up the hill. In my case, my legs were taking my 210 pounds up the hill. So there's an expression of its, well, and notice that's not force. We have to actually multiply that times 9.81 meters per second squared. So I guess I'll just do that right now, 2,000. Notice I haven't really read the question. I'm just trying to kind of think it through. Remember, in this book, we're technically saying 9.81. So this is actually 19,620 newtons. And notice I can't change that to kilonewtons because our units were Newton meters per second here. So I actually don't want to call that 19 kilonewtons, even though I could do that. So it's like, yeah, that's a heavy load. Well, what do we know about this? So I didn't even read the whole question. I just stopped at 2 megagrams and thought about it. And so it's going up a hill. Notice because it's going up a hill, I am bringing it up in the air. But remember, the issue is not how long the hill is. The issue is how high am I carrying it? It's at a constant speed of 100 kilometers per hour. That's not very good units either. Think about that. Why would that not be good? I don't really want those units to be the case. We'll talk about that in a second. And then notice its engine. Determine the power developed by the engine if the automobile has an efficiency of 65%. Wow. That means that 35% of the power that the engine produces is actually lost in the gears and friction and stuff that's inside the engine. Wow, that's kind of a bummer. I wonder if that's really true for kind of how cars work. So, So you should find this pretty confusing, and I want to try to give you a little bit of time to suffer here. But let's do one thing. Remember our time, our velocities. This is one of the things I need to show you. Our velocities were in meters per second, and I think I'll say this now. I said that power is Newton meters per second, or you could even think of that as newtons times meters per second. Notice another way to think of power then is, well, Newton is a force and meters per second is a velocity. So that's actually true too. Power can also be thought of as instead of work divided by time based on these units, it could be thought of as being force times velocity. So that's kind of interesting, because notice when velocity showed up there, you'd think, well, work and time, that didn't have velocity in it. But that is on my sheet as well. So notice my speed is in meters per second. So that's not good. I have 100 kilometers. Can you do this easily? Can you say, well, let's see, I got to get to meters per second, kilometers. So in 1 kilometer, there's of course 1,000 meters. So that would get me into meters. To get into seconds, I know there's 60 minutes in 1 hour, except for I can see I'm getting that upside down because I need hours to cancel. I need hours on top. So 1 hour has 60 minutes in it. That would get me into meters per minute, but then there are, in 1 minute, there are 60 seconds. And so I don't have to know much to kind of pull this off. That tells me now my unit will be meters per second now. And now I know what to do. I got to take 100, multiply it by 1,000. And then I got to divide by 60 and then divide by 60 again. And I get 2 point. That's not true, is it? 100, 1,000. Yeah, I get 27.78. So the units have got to be right. So I had a screwed up mass, I had screwed up speed, but that's how cars work. They, in other countries, are measured in kilometers, speeds are measured in kilometers per hour. It's not meters per second. So I got to convert this myself. Okay, so I've got those two things. I've got my force and I've got my velocity. So don't I just multiply those when I'm done? I want to give you a second to think about that.
We still have to worry about efficiency here.
Yeah, we still got efficiency. And notice it's traveling at a constant speed, so I can multiply those together, but what direction is the car being moved if I did that? In other words, what direction is this force in that I highlighted at the top? Because this is a much trickier problem than it first appears. That's gravity. So we're talking straight down. Well, the car is not going straight down, or I'm not lifting the car straight up. If I lifted it straight up, then I could take that force times that velocity and I would have power. And it'd be in watts because newtons times meters per second is watts. So that'd be lifting it straight up. Correct. Except for the problem is this car isn't going straight up. It's going up a 7-degree hill, of course. So I got to think about that. So makes me think I'm going to need a free body diagram just to kind of, we always kind of had to do that, right? In other words, this is my actual force going 16, sorry, 19, 620.
What if you were to just take the speed, multiply it by the cosine of 70, the sine of 7 degrees to find out how fast it's going straight up, and then just use like energy equations to find the rate of just using potential energy, and then from that divide that by the time it takes to change energies, and then you'll get the power that way.
Yeah, and that's the thing that I guess I'm interested in you realizing is how related all these concepts are. And so, yeah, there's, as long as you pay attention to your units, there's definitely more than one way to do this. And so the reality is my car is going this direction, right? Like this is 7 degrees. So that 7 degrees is also right here. It's the same angle. So you're right, I'm going to need to modify this. So this would be 19,620 times the cosine of 7 degrees. 19,620 times the cosine of 7. Am I in degree mode? Yes, I am. That's almost all of it. In other words, I'll just write it down here. That's 19,470. I think I'll round it off. It's 473.75, but I'll just call it 19,474. So 7 degrees is such a sliver of an angle that's most of it is actually going down into the ground. But notice the rest of it is actually trying to get it to go downhill. Of course, that'd be 19,620 times the sine of 7 degrees, and that's a much smaller number. That's 2391, approximately 2391 newtons. That's still a fairly decent sized number. But does it make sense? That's all gravity is doing as far as the car is concerned, since the car is actually traveling. Well, I'm going to call this the X direction. That's the X and that's the Y. Remember, I can kind of turn the axes any way I want. And so really what this is saying is that car is, gravity is only doing 2391 to this. So the the motor is actually overcoming that, not the 19,620 number, because it's not being lifted straight up. So is my free body diagram complete? It sort of has all of its forces in it. So I'll turn this one red just because. So there's 2 forces in it. The answer is no. There's the force of the motor. Because if it wasn't for the motor, wouldn't this be like the skier, the skater is just like skating downhill? And apparently the force of the motor is bigger than 2391 because it's actually making it up the hill, right? So how are we supposed to know what that number is? Because that's the force, that's kind of the force of the motor. Well, we don't need to do this, but let me just show you this just because I think it'll maybe make sense to you. So I'm actually calling that the positive direction. In other words, I have it angled. So isn't the sum of the forces equal to the mass times acceleration? But if we're working in X, then that'd be acceleration in X. So my forces are negative 2391 and positive force of the motor. My mass, we said, was 2,000 grams. 2,000 kilograms, I'm sorry. What's my acceleration in X though?
0, right?
Yeah, why, Landon?
Because its velocity is actually changing.
Yeah, they said it's a constant speed, so it was actually, and notice it didn't have to be sitting still, it just has to be a constant speed, so it's not accelerating. So that little statement they made there was actually pretty important. So that's actually times 0. So I guess in this case, the force, because I don't think this is obvious, the force of the motor then is actually counteracting. It's counteracting gravity, so it's effectively the same as gravity. If it had been increasing in speed, then I would have actually got a different number for that. The force of the motor would have had to be a lot larger. But that's all the force of the motor is doing then, is just taking care of that force. The ground is doing the other one. Does that make sense? Does it make sense? The ground is taking care of this one. So the normal force, I could add this in here too, the normal force of the, I'll say road, the normal force of the road is taking care of that. That's why I had to consider the sum of the forces in X and the sum of the forces in Y. And again, the car wouldn't be accelerating in the Y direction. And so those would be equal to, in other words, this is going to come out to be 19,474 as well. So my free body diagram was not even complete when I said it was complete. It actually has all 4 of those forces on it. And because it's moving at a constant speed, those are all going to balance each other. So the ground takes care of one of them. The motor takes care of the other one. So that's actually the force of the motor. Well, yeah, we know everything we need to know then to find power. Since power is better in our example, it's not so much work divided by time, but a force times a velocity. Well, I know that force now. So it's not 1960, it's actually 23. Force times velocity, it's actually 2391 for the force. And the units are correct with 27.78. So I have newtons and I have meters per second. So when I multiply that out, I get about, I'll do it just to make sure, 2391. I get about 66422. And again, that would be Newton meters per second, but we would be better to say watts. Now, they didn't say how to answer this. They just said determine the power developed by the engine. Well, this again, though, I think is important to understand. This is the output. The car actually is doing this. So does it make sense? This is the power output. The car is actually traveling. So this is the power output, not the power the motor generated. Again, I don't like the word input. It just doesn't sound right to me. It's more like the power that motor generated and then the power that the car actually puts out as a result of the transfer between the engine and the car. And so, you know, and again, how would I answer this? Well, because this is a car, it'd actually be better if I said this in, it'd be better if I actually said this in horsepower. So if I take 66,422 watts, what's the conversion for that? Well, we said earlier, I don't have it in front of me, but if I want watts to be gone and I'd like horsepower to show up, and this problem didn't say how to answer this. It didn't say it had to be in horsepower, but I think the answer in the back of the book probably is horsepower in this case. And we said on the note sheet that I showed you a minute ago that there was 746 watts in 1 horsepower. So I'm actually taking that 6642 number, 66422, and I'm dividing by 746. And so that's actually around 89 horsepower. So this is like 89 horsepower is getting the job done. So 65, I actually get 100, approximately 137. So Power of the engine is more like approximately 137 horsepower. That's actually the answer this question was asking for ultimately. That's kind of hard. I mean, there's a lot to think about there. So only 65% of what the engine produces, thanks to the gearing and so forth, is actually making it to the road. And making it to the road is kind of the important point.
It's also kind of interesting to think that the engine itself also is probably relatively inefficient in terms of getting the energy from the fuel.
Yeah, that's exactly right. Especially when you consider how archaic it is. It's literally an explosion. It happens inside there, which pushes a cylinder, and that cylinder is connected to the camshaft and so forth. And there's a whole bunch of connections in there. Yeah, that's exactly right. So
Yeah, and even the theoretical limits of how efficient an engine could possibly be still puts us like, yeah, what I believe it's like 64% for like the theoretically most efficient possible engine.
yeah, it's
And
not.
that's an engine that wouldn't really do anything in real life.
Yeah. Yeah, and especially when you kind of back it up even further and say, okay, you know, what percent of the gas's actual energy are you actually getting? But then you think, well, what did it take to produce that? You know, you had to get that gas out of the ground and so forth, and you got to burn it correctly. It actually makes a difference if you burn it in smaller molecules, like more of a mist. You get a lot more of it, your bang for your buck, if you will, if the carburetor mixes it with air correctly. And so it's a huge part of the way, I don't know a lot about that, but it's a huge part of the way advanced you know, race cars and so forth work, is getting that mixture from oxygen and gas, and then getting gas at the right sort of size. It's little spheres of gas, if you will, but you want it really misty.
There is still a huge energy loss going through the heat.
Yeah, that's right. And notice there's a whole bunch of heat loss. So yeah, you're exactly right. So yeah, it's kind of a terrible design ultimately. I mean, it seems strange to me that we're still using some, you know, kind of such an inefficient design to kind of, you know, do the job. So here's another example that's related, and you're going to see something like this in your assignment too. So that's why I wanted to hit it. This is more like what this is more like what you would do as an engineer. In other words, this is the way wells are drilled. At least that's one method, is just lifting up a heavy bar and just letting it pound down into the ground. So, you know, in the end, this is the work being done, is that thing needs to be lifted. But notice right over here, and this is the motor that's actually doing the lifting. And so, you know, again, there's a question of efficiency. I got the work output that needs to be done over here, but the motor's got to produce that. And now what things can you do that are kind of in your favor? Well, you can use gearing. Notice what's happening to this particular gear. And it says this in the problem, and I'll show you this in a little bit, but it's actually, this cable is tied here, and then they stretch the cable down to the end of this. It wraps around this, goes up here, wraps around another pulley, and then it goes down to the motor. Why would they do that? Does that change anything? Why didn't they just go up and over a pulley and straight down to the motor?
Is that doubles the force or something?
Yeah, let's think about this. Let's see, do we know anything over here? I might as well just use the right numbers. It said it's a 600-pound drill pipe. So this thing literally weighs 600 pounds. But think about just focus in on this right here. What does that mean? Each of these cables, since there's two cables right here, your free body diagram at that point right there, what does that mean those two cables are doing? To, well, statically not break. Does it make sense that since 600 is going down, 600's got to be going up? But look at that, there's two cables, which means each of them could do 300. Now do you see the brilliance of the design? So now follow this right side cable. If I follow the right side cable, that means that this motor is only having to lift 300 pounds. It didn't have to lift 600 pounds. Isn't that cool? So it's actually lifting a 600-pound cable based on the way this is designed. Now, is that free? Is it free to cut that in half? Is it free to cut that weight in half? What happens if you pulled on this cable 10 feet? What's going to happen to the drill over here as a result of
It
that?
lifts it up 5 feet.
That's exactly right. You got to cut the amount of weight you had to lift in half, but you also got half the work, or you had to double it. In other words, if you said, I want this thing to go up in the air 5 feet, well, now your motor's got to do double the work. And so there's energy is not lost. The motor's got to spin faster. And that's the brilliance of electric motors in our culture. Electric motors are really weak, but if you gear them correctly, they can spin really fast. And so speed is traded in for strength. That's kind of the idea. So this motor spins faster, but it doesn't have to lift as much weight. So this is a brilliant design. That's why this whole cabling concept is kind of an important idea. So anyway, what's the problem say? Determine the power output of the motor necessary to lift 600 pounds with a constant speed. Again, notice that constant speed thing. That's really good. 4 feet per second. Well, that's a velocity. And then they describe the cable as I was just describing. And so it's like, oh, it didn't really tell me that much. So what is it I do? Well, I say it said determine the power output. I know what power is. Power is either work divided by distance, or it is a force, just an equal sign, or it's a force times a velocity. That's my two choices. And since I'm given a velocity here, then I want to kind of work with the force times velocity version of this equation. But again, notice it said it's focused on the motor. So actually the motor's velocity is 8 because of that cable arrangement. And the force it was lifting was actually 300 pounds. Notice we'd have got the same answer if we did the other one. In other words, 600 pounds times 4 meters a second. We just still got 2,400 for this. So kind of either way we look at it, we get a power of 2,400 foot-pounds per second. So, there's my answer in a sense. That's what's happening here. Notice there was nothing in this about efficiency. It didn't say the motor was a certain amount of efficient. Again, it didn't actually say, like, that is a measurement of power in a sense, foot-pounds per second, but not really. Like the two units you'll use will be watts and horsepower. And that's why I showed you those examples a minute ago, because you're not going to be able to find a motor that does 2,400 foot-pounds per second. Like, that's not the measurement. It's horsepower. So, in the end, I need to figure out horsepower here. So again, let the units do the work. If I take 2,400 foot-pounds per second, and I think to myself, I would really like this to be horsepower, then I say, well, I know that 1 horsepower is, we said, 550 foot-pounds per second. And so there, yeah, if I multiplied it by that, then this weird unit would cancel with that one. So I'm dividing by 550. That's what it tells me to do. If I do that, I get about 4.4 horsepower. So these are both true. Does that make sense? Those are both the right answer. It's just that that's not how motors are measured. So you'll notice the answers in the back of the book of this section. On a test, I would say, tell me it in horsepower, just to kind of make sure you see that. But you can see in the real world, you'd want the answer in horsepower. So now I know what to do. So actually, that one of those motors on that table saw would have done this, right? There was a 5 horsepower motor on there. So can you see that you wouldn't want one of the disposal motors doing this job? It can't do it. Wouldn't be able to do this job. But that biggest table saw would. That's kind of cool, right? And you may have noticed in your own case in your life, if you lift something that's too heavy, it's really hard, and you don't want a motor to be at capacity. You would not choose a 5 horsepower motor to do this job. Does that make sense? You want something that can do it easily, right? Because then it doesn't wear the motor out, doesn't strain it so much. So anyway, that's just interesting. So you got a couple questions like this. These aren't terribly hard. But tricky. So anyway, did a couple book examples so that you feel good about that. The last thing I want to look at today is really this last part of chapter 14. So we had work and energy, and we had this formula, which is super significant. Initial energy plus work is equal to final energy. But as Daniel alluded to earlier, this concept of conservation of energy is kind of the same formula. Like this is kinetic energy. This is the words I used the other day. And that P is potential energy. Again, this should not feel totally new because of physics, but it's basically saying your initial energy of motion plus your work energy at the beginning will match the energy of motion and the work energy later, as long as nothing is lost. And that's again where this efficiency concept comes into play. Something can get lost. We'd lose heat. Heat is not being turned into your car going down the road. And so energy is not conserved in a vehicle. Like there has to be no loss in that system. So anyway, what does that mean? Let's look at an example. This may be all we have time for, but let's. I don't think I brought that in yet. Let me go get it. So it turns out this is a much easier, the conservation of energy is a much easier way to tackle these kinds of questions. Because notice this is well curved motion. I mean, I've got this cart that's going to cruise down here. Notice it's following a path that isn't even defined for us. Like it isn't saying that's some kind of an equation. It's just going down some ramp, and then it levels out for a while, and then it curves up here, and then it goes back around, it curves around here, and then hopefully takes off and nobody fell out of the car and everything's great. Well, notice that's following a very crazy curved path. And so in the previous sections, we have to know something about those paths. Like, what shape is that? What's the equation? If we don't have the equation, then we can't take its derivative and find the radius of curvature and all of that stuff that we needed to do. So the fact that I have the same energy, sort of the energy at A, and let's see if they even say this in here. Neglect friction. Is that the only thing they said about this? Yeah, I guess that's it. So neglecting friction, meaning we don't lose anything from friction. That means kind of the energy at A and the energy at B will be the same. Does that make sense? So let's just make up an example. This turns out to be a pretty hard question because they're asking us for the height, but like as an intro, let's just say H equals 25 meters. So I'll erase this later on, but basically let's just figure out what happens going from A to B. What happens going from A to B? We get down and do our first loop to loop, and we were sort of 10 meters higher than that. And notice the mass of the car makes a difference. Notice it's in kilograms. I'm very happy to see that I don't have to change it. And then they also gave us an initial speed. They told us that at A, there's an initial speed to this. And so basically conservation of energy is a great way to do this. So let's take a look. So, well, how much energy do I have at the start? Well, I've got two kinds of energy. I've got my kinetic energy, and I've got my potential energy, a force times a distance. And so what do I have there? Well, let's like figure out what we got. I know my mass is 700 kilograms. I know my velocity today. Notice the unit kilogram.
So just joules then, huh?
Meter. What'd you say, Landon?
Joule.
Yeah, that's right. So kilogram meter per second squared, and we renamed that yesterday a joule. So this is joules, 774,000 joules of electricity, of energy are at the start. And the concept of conservation of energy is it's going to be the same answer at B. Do you understand that? Same energy. So what happens at B? Well, let's go count that out. I have the same exact mass of the car. I don't know the velocity at B. That's kind of interesting. and I have a force and I have a distance. And so this is the energy at B, and they're going to be equal. So again, some of these things I know, like I know my mass, nothing has been lost. Nobody fell out of the car. I don't know my velocity at B. I still know my force. It hasn't changed. It's still 700 times 9.81. But notice my distance has changed. So I have less potential energy. So I only have 15 meters to multiply that. What does that tell you about the velocity then? If we lost some potential energy, then what happened to our kinetic energy?
It has have increased.
Yeah. Our potential energy's got to go up because this still has to be equal. Like this is still going to have to be the same energy as before. Energy is conserved. So these have to be equal. So this is going to allow us to actually find our velocity at B. Now, again, we did this before. We found our velocity. We were at the top of the ski hill and then we skied down the hill. But remember, that was kind of a challenge until we got this energy concept involved. And so notice these equations don't care how it got there. It's just, it used to be 25 meters in the air. Now it's 15. Game over. I don't care how it got there. Curved, loop to loop, who cares? So these have to be equal. Must be equal. So then I could say that 1/2 times 700 times the velocity at B squared plus, I'm going to multiply this out, 700 times 9.81 times 15 is 103,005. That's still got to be equal to 174,825. And so that's how I'm going to figure out my velocity. So if I subtract that 1,003 to the other side, and then I multiply both sides by 2 to get rid of the 1/2, I divide both sides by 700, I end up with the velocity at B squared is 205.2, which means my velocity at B raised to the 0.5 is 14.32. So the thing that I would not want you to be surprised with is the fact that it's bigger. Of course it's bigger. It's bigger. The other one was 3 meters a second, and this is bigger. Well, of course it is, because it traveled downhill a little bit. Do you understand if the car had just went straight there, it would be the same exact answer? Because it dropped 10 meters. Do you understand that because that's 14.32, the speed down here must be way high, it must be like 30 or something like that, right? Because it's on the ground, which means it has no potential energy. It's all kinetic energy. So it's going to be really fast in here. And then as it climbs, it starts to slow down again because it's trading its speed in for height. So if the question had given us a height and then asked us to figure out, what its speed was at B or at C, notice it just keeps going after this. And so it would even be going faster. Would you agree it's going faster here and fastest there because it's lower? Again, that's because no friction loss. If you lost friction, then that isn't necessarily true. Now, this asks us something, though, very difficult. I mean, ultimately, this is kind of the intro to this, but we're actually being asked a more difficult question here, which is find the height. So let's go back and get rid of that. What is that height they're saying? So let's read the question now. Determine the minimum height. Minimum height, what does that mean? Well, what would happen if the car came to a stop right here? Well, if this was not tied to the track, if it came to a stop right there, then that means that it would actually fall. This works as long as you go fast enough. Does that make sense to you? Like you could actually ride your bike around something like that as long as you didn't come to a stop, because your speed would keep you against the track. So this is saying determine the minimum height of the hill so that the car actually makes it through the loop-to-loop. Without leaving the track. So how in the world am I going to figure that out? Well, this is actually fairly complicated. There's a lot to think through. One thing I want to point out though is this: when it says without the car leaving the track, does it make sense to you that if everything is going well, there would actually be a normal force there? The car would be pushing on, or the track would be pushing against you. The car would be pushing against the track would be pushing against the car. So that's the direction that normal force would be. Again, it was easier to see like with the skier because, you know, here's the skier. And so, you know, of course the snow is pushing up against it. That's what's keeping them there. The only way that works in this example is if the normal force is actually pushing against the car. So, you know, in this case, it depends on where you are. As soon as I move to some other location, if I was over here, then the normal force would be pushing in that direction. If the normal force is equal to 0, does that make sense? You're about to fall.
I kind of don't like this problem very much. And the reason kind of comes down to what actual roller coasters are built, how actual roller coasters are built. Because anything that actually goes over a loop is going to be on our kind of an attached rail system. So instead of it being physically possible for it to fall, it would actually just kind of slide because you're just hard attached to it.
You're
Instead of being like
right.
on wheels.
You're right, but that's because modern roller coasters are safer than older ones, but they don't have to be attached. Like they make sure that you don't fall in modern roller coasters. But even the way this one is drawn, this is an old school one. So like I played with Hot Wheels as a kid. Did you ever have you ever played with those and they have a little loop to loop? Like the car just goes around there. And there's, you know, circus type of events where people are riding motorcycles around loops like that where you can fall. And so yeah, I totally get where you're coming from. So that's kind of code for this. And notice they even kind of give us a hint here. They ask us about the normal reaction on the car when the car is at B and when it's at C. And then they tell us, remember, this is code for radius. The radius of the curve is 7.5 and 5. That actually makes sense because notice those two shapes are basically circular. So wouldn't the radius of this right here be 5? And wouldn't the radius of this one be half of 15, which is 7.5? And so, you know, again, we don't have an equation this time. We can't take a second derivative and a first derivative and use that kind of cool formula we had. When I'm sort of glad I don't want to take a derivative of all of this. But they're kind of hinting that I'm going to have to think about that a little bit. Well, you may remember that since our motion here is not flat, I can't do what I did with the car a minute ago and talk about the sum of the forces in X and the sum of the forces in Y. I have to think now about the sum of the forces that are normal and tangential. Like I have to think about that formula because I'm curved motion. And of course, where I'm concerned with, if you are going to fall, it's going to be at kind of up here at B. Like if I get to where I am here and N is 0, the normal force is 0, then you're going to fall right there. So where we're actually interested in is where the minimum is actually up at the top. So we're here actually. So I'm going to call that the normal force of the track. If that's equal to 0, then that would give us a minimum speed. Do you understand that? I don't want that to be that close. I would want that number to be pretty big, like 100 pounds or something like that. But the question is, if I barely got there so that the track is not working at all, that'd be the minimum speed. Now the problem is though, isn't that also over here? Like which one is it? If you're going to fall, where are you going to fall? The first one or the second one? Well, it comes down to this right here. If this is the fastest speed, this is actually a slower speed. So if you're going to fall, it's going to be right here. Does that make sense? If you make it to here, if you made it to here, and say you were just barely going like 1 meter a second, does it make sense when you got here, you'd be going like 8 meters a second? So you're going faster. So this point right here is the one that I'm worried about. If I'm going to die, it's going to be because of this one. Do you understand that? because of those speeds. So my point is all of this is coming down to kind of what happens at B, not at C. So as per usual, let's think about the free body diagram of this. If I'm up here at point B, what's going on? Well, I've got gravity pulling down on me since I was a 700 kilogram car and 9.81 meters per second. That's gravity pulling down. So figure out what that is. That's 68, 67. So I've got that, but then I've also got the force, the kind of the Newton, the force of the track that's also pushing down. That's the normal force. So I think I called that N for normal before. I should be consistent. You agree those are both pushing the same exact direction?
Yeah.
So, well, let's look at our formula then. Remember, positive is inside, and so that means I've got both of those. I got the normal force of the track plus the 68, 67. Those are all of my forces in the normal direction. And then I've got my mass. And then what about acceleration normal? Is that 0? Because it said, did it say anything about that? No. Remember, acceleration normal was equal to v squared divided by rho. And on that track, on that portion of the track, we knew because it was circular that was 7.5. And we even knew our velocity. As a matter of fact, we knew it squared. So if I take 205.2 divide by 7.5, I actually get my acceleration normal to be 27.36. So that's not 0. Again, why is it not 0? Because the track is asking you to change direction. Remember, that's not a change of speed, it's a change of direction. And roller coasters are radically changing the direction that you're trying to travel. And so this is actually going to allow me to figure out the normal, kind of the normal force on the track, so to speak. Let's see. What is all of that? Actually, I did screw something up. That 205, where did that come from?
V sub B squared.
That came from when the height was 25. Remember, I actually don't know the height is 25. That was like just a practice problem, if you will. So that's not, I actually kind of filled in too many things here. So I'm going to go back here and write velocity at B there, but I actually don't know what velocity at B is. Does that make sense? Because I don't know what height is for height H, but I don't know what height is. So I'm just going to write velocity of B squared here over 7.5. But the key to this question is, does it make sense that if this is barely going to make it minimum, that means this is equal to 0? That's barely making it. Do you understand that? Like the track is not pushing at all. You are on the edge of dying here. If it was 0, you actually wouldn't quite make it, actually. So for that reason, the actual unknown in this question is actually v of b. I actually can know what velocity I'm at there that would actually produce this. So if I take 68, 67, I divide by 700, I multiply by 7.5, and I take the square root of that, I actually get the velocity at B is 8.58. Now, again, isn't that interesting? Because you might have thought the velocity for that would be 0. But notice what that velocity is overcoming gravity. It's overcoming that gravitational pull right there. So you're actually traveling there. You actually have a speed, but you still might almost fall. Do you understand that? If you went a little slower, you would fall because gravity is now overcoming the speed that you have pushing against it. So that's kind of interesting. So in a sense, then we have what we had earlier. It's just that we're sort of working backwards. That's why this problem was kind of so hard. It was kind of easy when we knew this height up here, but they're asking us what height would produce that. So if I go back and look at these equations right here, then it's kind of like I'm saying, well, I know now my final energy at B. So conservation, we're almost done. Conservation of energy. Again, I think it helps to kind of write the whole thing out. I've got my kinetic energy velocity at A not B. I've got my potential energy at A, so that's my sort of my A side, and then I've got the other side to consider, the B side. So I'm just going to write the same thing. Maybe I'll just copy it. Except for the only thing that of course changes there is the fact that we're talking about velocity at B. So what things do I know? Let's just start from what we know. We know our mass is 700. I'd like to do a couple of cool, tricky things here just to kind of like make you think a little bit. Force is mass times acceleration. My distance up here was, well, h. Like I didn't know what that distance was. My velocity, I did know. They told me that was 3. And over on this side, my cart hasn't changed, so it's still 700. I know my velocity at B. We just figured it out. It was 8.58. My force over here is also 700 times 9.81. And then my distance, because it was 15 meters off the ground. But as a time saver, do you notice every one of these terms has a 700 in it? So I could actually just leave 700 off of this. I don't think I will, but I could actually just cancel all the 700s, cancel all the masses, and just have a simpler problem to solve. But notice the whole left-hand side of this equation has a bunch of stuff, except for there's an h in it. So let's see, I have a half of 700 times 3, which is 1,050, plus 700 times 9.81. I think we already did that, but I forgot what it was. 68, 67. And then there's that h right there. That was the one unknown. The other side, I just have a bunch of numbers. I have everything. So 1/2 times I think I forgot to square this one. I just realized, so I'm going to write the right number in there. So the other half, I got 1/2 of 700, which is 350 times 8.58 squared. Plus 700 times 9.81 times 15. So I just have a number on that side. And so if I haven't screwed up, which I very well might have, so I can actually solve for h. Subtract 3150 from both sides. Bam, got a number. Divide by 68, 67. And I got 18.3. So velocity or height, that height is equal to 18.3 meters. Again, that should make sense to you because a minute ago when I set it at 25 meters, we made it, right? Like we made it all the way around. And so we know the normal force of the track at B is 0 because it barely made it there. But what's it going to be? Because it also asked, what's it going to be down there at C, right? So since it's going to be going faster at C, then what's that normal force? Quickly, because I know we're out of time here. So in order to get that normal force, I'm going to have to do the sum of the forces. The normal equals mass times acceleration normal. That's the formulas I'm going to have to use. And so what's happening at C? Well, I've got the normal force of the track pushing down. I've got that same 68, 67 pushing down from my free body diagram before. That equals mass times velocity at C squared divided by the radius. Isn't that what acceleration normal is? Is velocity squared divided by radius. So that's not good. This formula is not good because I don't know the normal and I don't know the velocity. But couldn't I use my equations to come up with the velocity so that then I could find the normal? So I could choose any point I want to compare it to. I could choose B to compare it because I know everything about that. I know what speed I was going there. So I think I'll go from B to C to figure this out. I'll conservation my energy from B to C. So 1/2 times mass times velocity of B squared. I did say I knew what that was, right? Velocity of B is 8.58. So I'm just going to plug it in since we're kind of hard on time here. 8.58 squared plus force, which is 68.67 times the distance of 15 meters off the ground. That's what was going on at B. So this is kind of like the energy at B. What's the energy at C? Well, it's still 1/2 times 700, but times the velocity of C squared. I don't know what that is. Plus the same 68.67, but times a distance of 10, because that's only 10 off the ground. And so this is the energy at C. And notice I like this equation because it's only got one unknown in it. So I end up with velocity of C being about 13.1. Not surprising because the velocity at B was 8.5. And so this would be faster because we lost some ground. And so now I can take my 13.1, pop it back into this equation over here, and I end up with the normal of T being about, the normal of T at C being about 17,173 newtons. Surprisingly large number. You should feel a little bit overwhelmed right now. Actually doesn't look right to me. You should feel a little bit overwhelmed. Like this is kind of what makes physics hard. You just kind of feel like you have formulas running everywhere in your head. So you're definitely going to need to spend a little bit of time with this. See if you can make sense of it. Anyway, I need to shut up. We're way over time. So I will post everything. And if you want to, as always, if you want to send me an email or text and say you want to talk about some particular problem, but I tried to do this time just because we had to cover so much in one session. I tried to do examples that were similar to what you have to do in your assignment. So you'll probably help if you look these over. So. All right.